Okay, so an ant walks forward 1 unit and then turns to the right by 2 pi by 9 radians. It repeats this a further 3 times. Show that the distance of the ant from its initial position is as given. Okay, so instead of turning to the right, I'm going to picture him rotating to the left. Actually makes no difference, but for the purposes of keeping the numbers positive and easy, we'll just imagine the situation as follows. So he walks to the right by 1 unit, rotates through 2 pi by 9 radians, walks straight for 1 unit, so that angle's 2 pi by 9 radians, and then from where he's facing, he rotates a further 2 pi by 9 radians, and then continues to walk 1 unit. So that's 2 pi by 9, and that's another 2 pi by 9. So in total, it's 4 pi by 9 radians to the horizontal. He's done it once, twice, and now another time. So this is his third time that he's repeating it. So again, rotating through 2 pi by 9s and walking 1 unit. So that's going to be 1, 2, 3 rotations. In total, that's 6 pi by 9. And we want his distance from its initial position. So if we look at the horizontal distance, just the horizontal, we can see that it's 1 plus this distance here. We can see that this distance here is simply 1 times the cosine of 2 pi by 9. And then this distance here is 4 pi by 9, etc., etc. So this is the horizontal distance that the ant is displaced at. He ends up here. Of course, cosine of 6 pi by 9 is going to be a negative number in the second quadrant, so it makes him move backwards a bit. So this quantity is a negative number, but that's not important at the moment. The idea is that he ends up horizontally. He is displaced this much, and vertically, by a similar argument, it's going to be this distance plus this distance plus this distance. In other words, sine of 2 pi by 9 plus sine of 4 pi by 9 plus sine of 6 pi by 9. And if we want to look at that as a position vector, we can see that that is the ant's position vector. And if we can find out its position vector, then of course it's just the modulus of this number is what we're looking for. Okay, so if we now look at this position vector as a complex number, okay, it's quite easy to see that that is represented by the real part plus I times the imaginary part, or the y part is our imaginary part right here. Okay. Now we are reminded that e to the I theta is equal to cosine theta plus I sine theta. Now we can see that this and this matches up, and therefore we can just match this and this, where if I said theta is equal to 2 pi by 9, then this and this, using this identity, Euler's identity, leaves us with this, and this is going to be 2 theta, 4 pi by 9, and that is 3 theta, where theta is 2 pi by 9. So this is the sum. Z is its final position. Imagine it's a complex number. Then we just need to find out what Z is. And we want the modulus of Z eventually. And this is just a geometric series with first term 1, common ratio e to the I theta. And there are 1, 2, 3, 4 terms. So we can use the usual formula for the summation of a geometric series, and that's given here. And so we just substitute those details in. So Z now, this complex number, can be represented as this fraction using this formula. And now let's look at this. Now, there is one important formula that we could use here to simplify this. And it's quite a fundamental formula we use which is this identity right here. This is very important because I'm now going to try to somehow force this from this. That's the key to this question. And actually, it's just down to a simple factorization. So I'm going to factor out e to the I 2 theta. And let's see what happens when I do that at the top. When I do that, this times this takes me to this, and this times e to the minus I 2 theta becomes e to the naught, which is 1. Okay, and by a similar argument, if I factored out e to the I theta over 2, this times this leaves me with this, and this times this leaves me with, again, e to the naught, which is 1. And now we're just going to tidy this up. So just as we would with normal fractions, we're going to now simplify this. So when we divide, we subtract the powers. So that's going to be 2 theta minus theta over 2. So that leaves me with 3 theta over 2. This, I'm going to use this identity, but instead of theta, I have 2 theta. And instead of theta, I have theta over 2 here. So I'm just using this identity for this part. And we end up with that. And now we're almost done because we just need to work out the modulus of z. Well, here's z, and we want the modulus of z. And we are reminded of one more rule, which is that the modulus of z1 times z2, where z1 and z2 are complex numbers, is the same as the modulus of z1 times the modulus of z2 separately. So here we observe that this number has a modulus of 1 because the coefficient, remember, it's re to the I theta, where r is the modulus of a complex number. So here there's a coefficient of 1, so that the modulus of this number is 1. So we can actually ignore it altogether, and we end up with this. And we just go back to our substitution. Since theta was 2 pi by 9, we're just going to substitute it in. And we can see that the two i's cancel out nicely. And because the modulus of this number, because those numbers are both positive, it's just a real number. So the modulus of a real number, we can ignore the modulus sign, and we have the result that we require. And that's the end of the question.